Hello, my name is Mike Lichtart and I'll present our paper on behalf of the Sorokova Consortium. The COVID-19 pandemic affected more than our health. It also had a negative impact on education. It caused a lot of deficiencies in math, disproportionately affecting vulnerable children. This is the starting point for the Sorokova project. The potential for social robots in education is well established, although math education in particular is somewhat underrepresented in the research. The applications that exist often rely on a tablet-child interaction, where the robot is standing to the side, occasionally offering feedback. However, research also shows that social behaviors of the robot can distract from the educational task. The question then becomes how to better intertwine the social behaviors of the robot with the math task. When taking a social constructivist perspective, it makes sense to include those social behaviors because learning itself is inherently a shared and social process. People learn through social interactions. Feeling a connection with your teacher is an important factor for success. Research shows that children learn better from more familiar agents, and if they can relate to a non-human agent, they are more motivated to learn from that agent. The closer the children feel to a robot, the more interested they are to keep interacting with the robot. And this is key for the long-term effectiveness of a robot math tutor. In our implementation of the robot tutor, we use the math instruction theory called realistic math education. Key is that the math is grounded in a reality and that the math education is active and interactive, learning by doing together, and that the teacher offers guidance at the right time. Additionally, math education literature also suggests that the experience of success is key for the math performance of children. So we set out to design a math tutor where the interaction intertwines the robot's social behavior with the math task, contributes to the relationship formation, provides a grounded reality for the math problems, scaffolds the learning process by providing guidance at the right time, and providing children with an experience of success. The basis of this interaction is a social conversation, where the child and the robot chat about interests and hobbies, and the robot shares about its fictional past and its jobs and its friends, and multiplication problems are part of these anecdotes the robot shares. So this is how the social and educational components are intertwined, and it also provides a fictional reality to ground the math problems in. The robot asks the child for help and checks the math at the end. There is no judgment by the robot after an incorrect answer, and the robot praises the effort and not the answer. So let's look at an example of one of these math interactions.
Ik was laatst op een groot voetbaltoernooi. Ik moest bijhouden hoeveel sporters er waren. Er waren 5 verschillende teams. In elk team zaten 13 sporters. Hoeveel sporters waren er op het voetbaltoernooi? Dus hoeveel is 5 keer 13? Druk op mijn teen onder het groene lampje als je het antwoord weet. Wat is 5 keer 13? 65. 65. Ja, volgens mij ook. Goed gedaan.
For this math interaction, we developed 3 modules. The first module adapts the math level based on the child's performance. The problem gets gradually more difficult when giving correct answers and swiftly easier when giving incorrect answers. The second module focuses on personalization. We use a memory-based personalization strategy we developed previously and presented at HRI last year. The robot remembers and refers to the child's name, hobbies and interests to make the conversation more personal. The topics of the math dialogue are matched with the child's interest. Co-creating a secret handshake together is a well-appreciated feature as well. The final module adds scaffolding to the interaction. Using an RME method called progressive schematization, children are offered guidance by the robot. The key of progressive schematization is the relationship between numbers and working with informal strategies. For example, 14 can be split into 10 and 4, which are easier numbers to work with if you know your basic tables. And these same patterns can be used to solve math problems. Whenever the child makes a mistake or gets stuck, the robot uses an appropriate informal strategy to break down the problem into steps, and the robot does this verbally and visually using the tablet. and children get another chance to solve the problem using this breakdown. Based on the rationale just presented, we hypothesize that scaffolding and personalization will increase children's math performance. We furthermore expect that personalization will increase the social presence of the robot and feelings of friendship. We only expect that scaffolding will increase the social presence of the robot, but not necessarily feelings of friendship. To test these hypotheses, we ran a user study on 6 different schools. For 130 participants, we have complete data and those are included in the analysis. Each participant interacted 3 times with the robot within a week period, and each interaction lasted approximately 17 minutes and was filled for about 80% with math dialogues. We used a 2x2 between subjects design with personalization and scaffolding as factors, and we measured math performance and the robot sociability as dependent variables. Let's look at the results. The performance scores between the personalization condition were not statistically significantly different. There was a significant effect of scaffolding on performance. After the first session, participants made less mistakes and were faster to solve math problems in the scaffolding condition. The question, however, is what part of the scaffolding caused this effect? If we look at the results, they are generally high, likely a result of the easy difficulty level. This also means that children were not exposed to the guidance content a lot, so it's unlikely that children improved their solving strategies from just these few exposures. However, the consequence of making a mistake is lower in the scaffolding condition, because the robot offers help and a second chance, instead of just moving on to the next problem. It might be the case that this boosted children's math efficacy, which is an important factor for improving math performance as well. This is a hypothesis that is left to test in future work. Let's move on to the robot sociability. The social presence scale was not reliable enough, so we analyzed individual items separately instead. The results showed that the robot felt more alive to children when it offered guidance. When the robot did not personalize the interaction, children attributed more feelings towards the robot when it offered the guidance. So it appears that overall, the scaffolding behavior increased the social relevance of the robot. The feelings of friendship scores were so high across the board that we did not find a statistically significant difference. We did an analysis of the individual items as well. That analysis revealed that children feel the robot is more like a friend in the personalization condition. To conclude, in our paper we presented a validated design specifications for a social robot math tutor that intertwines the social and the educational components. The concrete behaviors that we provide increase math performance and make the robot more socially relevant. It brings us a step closer to offering teachers a new tool to address the educational backlog caused by the pandemic. Thank you for your attention.